Here they ask us to interconvert numbers of atoms and mass of compounds. We are converting from one thing to another. Here's our substance, tetraborane. And it says that it contains 1 billion hydrogen atoms. This sample of tetraborane has a 1 billion hydrogen atoms. Now, of course, there aren't 1 billion hydrogen atoms in one molecule of this, but of course, molecules are very tiny. So we have a rather large sample, or significant sample of this, and there are 1 billion hydrogen atoms. It says, what is the mass of this sample that has 1 billion hydrogen atoms? So we've got to do some converting here. So where do we start? We start with what we are given. Our starting point is atoms of hydrogen. And we need to get to a mass of the compound. So 1.0 times 10 to the 9 hydrogen atoms is where we are. So what's the first thing we need to do? Let's map out where we're going. So we're starting with atoms of hydrogen. If I can get to a molecule of this substance, then I could get to moles of this substance and then to mass. So let's look at what we may need to get there. To get between moles and mass, we should know that the conversion factor needed is molar mass. That'll help us to convert from moles to mass. What about to convert from molecule, or number of molecules, to moles of this substance? Our conversion factor to get between molecules and moles, or this could also be atoms in moles, or formula units in moles, is going to be Avogadro's number. Avogadro's number is our conversion factor that tells us how many of these are in a mole. So we have molar mass that'll take us from moles of this substance to the mass of this substance, or this sample. We have Avogadro's number that will take us from a certain number of molecules of this sample to moles of this sample. We need to be able to get from atoms of hydrogen to how many molecules it corresponds to. Well, we could use the chemical formula in order to do that. So we're gonna build a conversion factor here from the chemical formula itself. So we'll put the chemical formula here. Let's see how we build this one, this conversion factor. So we have B4H10. Let's build our conversion factor. In one molecule of B4H10, how many hydrogen atoms are there? There are 10 hydrogen atoms. Here is our conversion factor. It relates atoms of hydrogen to number of molecules. One molecule, 10 hydrogen atoms. So we have this conversion factor. And then when we get to molecules of this substance, we can use Avogadro's number to get us to moles of the substance, and then we can use molar mass to get us to a mass. So let's do the problem. Our first conversion factor, we're going to place 10 hydrogen atoms on the bottom and one molecule of B4H10 on the top. Next, let's multiply across our second conversion factor. Now we are at, if you notice, hydrogen atoms cancels and we're at molecules of B4H10. Here we are. Now we need to get to moles. We need Avogadro's number to do that. So what is that next conversion factor? Well, 1 mole of B4H10 is equal to 6.022 times 10 to the 23 molecules of B4H10. That's our second conversion factor. Where is 1 mole going to go? Up top, 1 mole of B4H10 is equal to Avogadro's number of molecules. Of B4H10. Notice how the units of molecules B4H10 cancel out. Now we have moles of B4H10. If we stop now, we'll have an answer in moles, but we want mass. We need one more conversion factor. And this last conversion factor is going to relate moles to mass. It's going to be the molar mass. Do we have the molar mass of B4H10? No, they didn't give it to us. We have to find it. So let's go to our periodic tables. We have B4H10. All right, so the molar mass is going to be equal to the molecular weight. So boron, we have 4. For boron, we have 4 boron atoms, and each atom has an atomic mass of 10.811. For hydrogen, we have 10 of them, and each one has an atomic mass of 1.0079 AMUs. So let's get the molecular weight, which would be equal to the, numerically equal to the molar mass. So we have 4 times 10.811 plus 10 times 1.0079, 55.3, well, that'd be 53, excuse me, 53.323 ANUs. That's the molecular weight. The molar mass is going to be the same value, 53.323, but the units will be grams per mole. So we place that here. 1 mole of B4H10 has a molar mass of 53.323 grams of B4H10. Moles cancels, and now we are left with grams. So let's do the math here and see what answer we get. I like to put this into my calculator exactly how I see it, so I will type 1.0 times 10, or capital E, to the 9, open parentheses, 1 over 10, close parentheses, open parentheses, 1 over Avogadro's number, 6.022 times 10 to the 23, close parentheses, open parentheses, 53.323 over 1, close parentheses. I get a value of 8.8546 times 10 to the negative 15 grams of B4H10. So even though it seemed like a large, like it would be a large sample because we have a billion hydrogen atoms, we kind of get an idea of how small molecules and atoms actually are. If I have a billion hydrogen atoms, I only have 8.8 times 10 to the negative 15 grams of this substance. So you can't even measure that out. That's an extremely small amount. But we have a billion hydrogen atoms. So this is our answer, but we want to round it to 2 significant digits. So this would be 8.9 times 10 to the minus 15 grams of B4H10.